You know, from the remote on your coffee table to the phone in your pocket, our entire lives basically run on batteries. They are the silent, unsung heroes of the modern world, for sure. But have you ever stopped to wonder what's actually going on inside those little metal cans?
I mean, it really does seem like magic, doesn't it? This little self-contained object that can just light up a screen or start an entire engine. Well, it's not magic. It's chemistry. And we are about to pull back the curtain on these tiny electrochemical engines. So, what is a battery, really? At its absolute core, it's a tiny device designed to do one thing and one thing only: turn stored chemical energy into electrical power. And it does this using a very specific, very controlled chemical reaction. Let's see how that all works.
So here's our game plan. We're going to start with the secret engine that's inside every single battery. Then we'll look at the difference between disposable and rechargeable power, pop the hood on your car battery, and finally, we'll take a peek into the future with fuel cells.
Okay, so first up, the secret engine. And what's wild is that every battery, whether it's a tiny one for your watch or a massive one for the power grid, it operates on the exact same principle. It's all about controlling a flow of electrons.
I want you to think of it like a controlled waterfall. At the top, you have the anode. That's the negative terminal. A chemical reaction here called oxidation releases the stream of electrons. Those electrons, they have to go somewhere. So they flow through your device, that's the external circuit, kind of like water turning a wheel to get work done. Finally, they arrive at the cathode, the positive terminal, where another reaction scoops them up. And that continuous flow, well, that is electricity. All right, let's talk about our first category, those everyday disposable batteries. You know, the ones you buy in a big pack. Chemists call them primary cells, and they're designed for a one-way trip. Once that chemical reaction inside is finished, that's it, the battery is done. And this is the classic workhorse. The outer casing you feel, that's actually the zinc anode, the negative terminal. Inside, there's a graphite rod that acts as the cathode, the positive side, and they're separated by this moist paste called an electrolyte. Now, here's the crucial thing to understand. All of these sizes, AA, AAA, C, D, they all produce the exact same 1.5 volts. The only difference is the bigger ones are just packed with more chemical fuel, so they last longer. That's it. Then, in the 1950s, the dry cell got a major upgrade, the alkaline battery. And just like the name says, it uses an alkaline electrolyte instead of an acidic one. The result was a total game changer. We're talking 3 to 5 times more energy and a much more consistent voltage output while it's being used. This is why they totally took over, even though, yeah, they can still leak that crusty stuff sometimes. But what about the batteries we don't throw away? Well, that brings us to secondary cells, which we all know as rechargeable batteries. The magic trick here is that their chemical reactions are reversible. When you plug them into the wall, you're applying an external current that basically runs the chemical reaction backward, resetting them so you can use them over and over again. Now, there are a few key types out there, each with its own specialty. You've got the tough nickel-cadmium with its jelly roll design that gives you the big jolt of power needed for things like power tools. Then there's the heavy, cheap lead-acid battery. That's the workhorse for cars. But the real star of all modern electronics, the one that truly powers our daily lives, is lithium-ion. And this number right here is why lithium-ion completely took over the world. A single cell puts out around 3.7 volts. That's more than double a disposable alkaline battery. This incredible energy density lets us pack a huge amount of power into a tiny, lightweight package. It's literally the reason our smartphones and laptops can even exist. Ultimately, their success really just comes down to this perfect combination of features. They provide a ton of current, they're incredibly lightweight, they give you a nice steady voltage for consistent performance, and they hold their charge for a really long time on the shelf. This is what makes them the undisputed king of portable electronics. Okay, let's switch gears and talk about a special case, that big, heavy block under the hood of your car. The lead-acid battery is a true workhorse, and it's built in a totally different way from the small batteries we've been looking at. So how does this thing produce so much power? Well, a car battery isn't just one giant cell. It's actually a box that's hiding 6 smaller cells inside. Each one of those produces about 2 volts. And by connecting them in a series, positive to negative, over and over, their voltages just add up. 6 cells times 2 volts per cell gets you that powerful 12-volt battery your car needs to start. So you might be wondering, why on earth do we still use this old, heavy technology that's filled with corrosive acid? It's simple, really. It's cheap to make, and it is exceptionally good at its one main job, delivering a massive, massive burst of current to turn over a cold engine. No other battery can provide that much starting power so reliably for such a low cost.
All right, for our last stop, let's look beyond the traditional battery to a related technology, the fuel cell. These are sometimes called flow batteries, and believe me, they operate on a fascinatingly different principle.
Okay, here is the crucial difference. A battery is a closed system. All the chemicals it needs are sealed up right inside. When they're used up, the battery's dead. A fuel cell, on the other hand, is an open system. It's much more like an engine. Reactants like hydrogen and oxygen are fed in continuously from an external tank. As long as you keep pumping in the fuel, it just keeps generating electricity. And this is where you really see the advantage of a fuel cell. A typical gas engine is incredibly inefficient. Only about 20 to 25% of the fuel's energy actually moves the car. The rest is just wasted as heat. A hydrogen fuel cell, by contrast, is 50 to 75% efficient. It converts way more of the fuel's chemical energy directly into useful electricity, with plain old water as the main byproduct. So from that simple dry cell to advanced lithium ion and these super efficient fuel cells, these tiny engines are constantly evolving. They're getting lighter, more powerful, and way more efficient. And as our demand for portable, clean energy just keeps growing, it leaves us with a really compelling question. What kind of tiny engine is going to power our world tomorrow?